conversion of solids. That is what we are going to learn today. So let me run a very simple experiment. The experiment is, let's say you take 1 liter of water, and let's say this is my cylinder in which the water is at this moment, right? And then you are pouring this water into a container, and the shape of that container is a cube, right? So what happens? You can tell very easily that the water which is in the cylindrical shaped container will take the shape of the container into which it is being poured. Exactly, right? And if you were to do the same thing, the same 1 liter water, if you pour into a container, and let's say that container is conical in shape. So what happens? The water will take the shape of this container, the one that is conical in size and shape, right? So what's the idea? Why we are talking about pouring water and all of those things? And how is this linked to conversion of solids? So the idea is this. Think about that if you were to take any solid and if you were to melt that solid down and then you convert that solid from its original form into a new form, whether it is cubical or whether it is a conical form, right? What remains constant in this conversion process, so this is called the conversion. What remains constant in this conversion process is the volume, right? Even though the shape and the size and all those things will change, it is the volume that remains constant. And that is precisely the purpose in this tutorial, that when we talk about the conversion of solids, we are talking about literally the conversion of volume from one shape into another shape, right? Assuming that we are not altering any other properties of that material, such as density or any of those things, right? So to better understand, let's go take a look at some examples to help explain this topic a little better. So take a look at this example. What we have is a solid metal cylinder of radius 21 centimeter and height 14 centimeter is melted and recast into spheres of radius 6 centimeter. We need to find how many spheres can be made by this conversion, right? So let's put some dimensions here. So we have a cylinder, the radius is 21 and the height is 14, right? And let's say this is my sphere, the sphere having a radius equal to 6 centimeter. Okay, so what exactly we are doing is we have a cylinder and we are converting that into a spherical ball, right? If the volume remains constant, that means whatever is the volume of the cylinder, it will remain constant and we can convert that into the volume of a sphere. But the sizes of these objects can be very different, right? And we know that a sphere has a smaller size compared to a cylinder. So if there would be n number of spheres, then n times the volume of each sphere should be equal to the volume of the cylinder. Okay, so this will be equal. So our objective is to find this value, the n, the number of spheres that can be made. So we'll say that n is equal to V1 divided by V2, right? Where V1 is the volume of a cylinder and that is pi r1 square h, and V2 is the volume of a sphere, that will be 4 by 3 times pi r2 cube, correct? These are the simple formulas for the volume of each one of these shapes. So let's cancel few things here. So pi cancels and what you get is finally this is 3r1 square h divided by 4r2 cube. So let's plug in these values. So it will be 3 times r1 is 21 square times h is 14 divided by 4 times r2 is 6 centimeter, so cube of 6. So as we calculate this value, this gives you equal to 21.4. Now this means that we can make these many spheres, 21.4. Now you cannot make half of a sphere, so sometimes we ignore this partial value and we say that it is only the 21 spheres is what we can make in this conversion process. Or to be precise, we can make 21 and 0.4 of a sphere. So the key principle in this entire discussion is that as you are converting from one object into another, one thing that remains constant is the volume. Alright, so let's take a look at this example. We have that a hollow sphere with the external radius of 6 centimeters is melted and recast into a conical shape with the radius 2 centimeter. So this is my sphere. let's say this is a hollow sphere. It's not completely filled with the solid, right? So this is my sphere, right? So there are two radiuses. One of them is this radius, let's say that is external radius R1, it is 6 centimeter. And then there is internal radius from this center all the way to the internal core. And that value is R2, let's say that is unknown. We need to find that. So once you convert this volume into a conical shape, it is completely filled with the metal that comes from this hollow sphere, okay? So the radius of this, let's say it is just simply R. This radius is equal to 2 centimeter with a height of 91 centimeter, okay? We need to find the inner radius of the shell. So what remains constant in this conversion? What remains constant is the volume. That means we need to find what is the volume of this hollow sphere. Let's say that is V1. So that volume will be what? The volume will be 4 by 3 pi R1 cube minus 4 by 3 pi R2 cube. Now why exactly we came up with this formula? The reason is we need to calculate the volume of all the space that is contained by the metal, right? And that will be a difference of the smaller sphere versus the larger sphere, right? So if this is the volume of the smaller sphere, which is the internal radius sphere, and then that is the volume of the external sphere, then the difference of these two will give you the volume of the sphere that contains exactly this much metal, right? Now, this volume is the volume of sphere. Since it remains constant, we need to calculate the volume of this cone. That will be V2. Let's say that volume is 1 by 3 pi r square h. Now V1 is equal to V2. We maintain that value because we are converting. We are not losing any metal at all. So these two volumes have to be equal, correct? That means let's solve it here. 4 by 3 pi r1 cube minus r2 cube is equal to 1 by 3 pi r square h. How did I get this one? Is simply by applying the reverse distributive principle on this expression. 4 by 3 and pi are common. They come out, right? And what remains inside the parenthesis is r1 cube minus r2 cube. So now let's cancel few things. 3 cancels and pi cancels. And let's substitute everything that we know of from this expression. So what remains from here is 4 times R1 is 6 cube minus R2 cube is unknown. This is equal to R square, which is 2 square times H, which is 91. So once again, 4 cancels with this 2 square because they are equal. And let me take it from here that 6 cube minus R2 cube is equal to 91. Or you can say that R2 cube is equal to 6 cube minus 91, and that will be 125. Or when you take the cube root on both sides, you will say that R2 is equal to 5 in centimeter. So very simply you got your result. The internal radius that we needed to compute right here, that is 5 centimeter, right? So the key point, what we need to take home from this exercise is that as we talk about the conversion of solids, we are talking about it is the volume that remains constant as you convert from one solid into another solid. So with that, we pause here and you should proceed on to quiz and exam modules to develop a good understanding on this topic, the conversion of solids.